So this is Math Mornings at Yale. We've been running this for, I guess some of you have been coming for since last year. This is our second season. The idea is to talk about mathematics, the patterns and the thoughts and the ideas of mathematics in some kind of way that people can appreciate. And this time, so I usually get my colleagues to come and give lectures, but this time I convinced myself. So I'll be giving the lecture. And I think we're ready to go. So, all right. So today's talk is about infinity. But I thought as a warm-up, we could maybe start with some finite things. Oh, hi. So just sort of for practice. Actually, but I wanted to ask, the first question I had to think about is, how many people are in the room? Anybody want to take a guess? Yeah? How much? 150? 250? Over there? 113. Okay, so we're all right around 150, 113. What? Is there another? Oh, okay. Any other guesses? I actually don't know the answer, I should tell you. In fact, I imagined it would be a smaller number than it actually is, so I'm already kind of... Any other guesses? 85? 110. Okay, 110, 85. All right, so... and the way we would find out if we were trying to be really careful is we would maybe count, right? If we could, maybe we would start, you would say 1, and you would say 2, and you would say 3, and so on, and we get through everybody, and we'd know exactly. Okay. How many chairs are in the room?
160.
160? Did you count? Yeah. 160. Excellent. 160. Okay, so and then can we count the chairs in an easier way than we would count the number of people? No. What? Any ideas? Count the empty chairs. Rows and columns. Anything else? You said that? Yeah, rows and we can count. We can count a row and count how many rows there are. Multiply. And maybe actually we do that, but then there's a few extra chairs in the back, so we have to fix it. But there's patterns, right? There's some geometry, there's some patterns that tell us how to count this. Okay. One last thing about this. Which number is bigger, the number of chairs or the number of people? Number of chairs is bigger. Okay, by the way, just barely, but in fact, so how do we know the number of chairs is bigger? This is not supposed to be a hard question, but how do we know without counting that the number of chairs is bigger? Yeah? There's empty chairs. So let me see. So let me write that down. Empty chairs. That's one thing about why there are more chairs than people. What else we need to know? We need to know something else. Yeah? Nobody's together, right? One person per chair. I'm sorry, what? Nobody's standing, right, okay, sorry. So, in fact, every person has a chair, nobody's standing. Actually, somebody is standing, but let's pretend nobody's standing. Everybody has a chair. Everybody has, so everybody has a chair. No two people have the same chair, I think. Oh, no, 2 people have the same chair. 3, oh. So, by the way, this is the difference between math and reality. But we're talking about math. So, in the math version of the room, everybody has their own chair, and everybody has a chair, and there are empty chairs, so there are more chairs than people. Okay? All right, that was the end of the people and chairs. What else can we do? Let's try to find a bigger number. How many red blood cells are in the room? Any guesses? Yeah.
Well, there's more than almost a million cells in a person, so if there's 150 times a million, that would be...
I'm just getting an eraser.
I'm doing math in my head.
So 150 times a million. So you want to take the number of cells. That's not so bad. Okay, let's see.
I would say
100 and so you want to say 150 times a trillion. How much is a trillion? That's like...
That's 6 zeros.
6.
No,
Wait. That's 1,000.
Yeah.
That's a million. That's a billion.
12 zeros.
12 zeros. That's a trillion, right? Did I get that? I'm running out of room here. Okay, so that's 10 to the 12th. Did I do that right? Okay, so that's a guess. Let's see. Actually, I looked this up. I could ask my wife. Yeah, that's true. I always do. Yeah, so I looked it up on the web, and they say that there are 20 trillion blood cells, red blood cells, in the human body on the average, more or less. So 20 trillion, and so this is about right? This is 1 trillion. So maybe it should be 20 times that, right? So 150 people times 20 times 10 to the 12th. How many red blood cells are in the room? Okay, that's a good estimate. Okay, now so good. I have a couple more examples of big numbers. This is a first attempt at some other kind of way of counting things. Suppose I was going to choose 2 volunteers in the room. Okay, then people would raise their hands, and I would choose 2 volunteers, and they would come up and do something embarrassing. So if I were to do that, how many different ways can I choose 2 volunteers? Yeah?
By order of their name and raising hand.
Oh, so these are different methods for doing it.
Yeah.
I could order everybody by alphabetical order and then choose the first 2.
And
I could raise their hands.
computer version randomly.
Okay. I could randomly choose. That's right. Yeah? Oh, whichever. You first and then you. Go ahead. It'd be a lot like the number of people squared. Yeah, the counting of how many different ways of choosing 2 volunteers. Is that what you wanted to say also? All right.
So wait, the question is how to find 2 volunteers?
No. So that was the question you were answering. Is how do we do it? But the other question is how many different outcomes can we get of having 2 volunteers? So now I heard a couple of things. Yeah. About 11,000. Yeah, if we have 150 people, how did you get 11,000? All right, now we need somebody else to. So, how about you over there? Say again? 150, very good. Let me write that down, because I think a bunch of people wanted to say this. 150 times 149. Why is that? Anybody want to say? Yeah, well, you use your.
Because once you choose 1 volunteer, then there will only be 149 others.
Right. 150 choices for the first volunteer, 149 choices for the second volunteer. There's actually one trick here. There's one issue. Yeah?
If you have 2 people, you can only have the same pair of people once. If you flip them around, that would be technically another pair.
Okay, you're right. I'm distinguishing between the first volunteer and the second volunteer. So if I care which one I called first, then this is the right number. But maybe I just care about which 2, and I just want them to dance together, and it doesn't matter who is first. Then I should divide by 2, right? Because I've counted each pair of volunteers this way and that way, right? So I should divide by 2. Okay, that's a number that's on the order of what? 11,000, right? Maybe. Yeah. Let's write 11,000 and hope that's about right. Because since I'm going to talk about infinity, I don't have to worry so much about 11,000. Okay, one more like that. Suppose that we were going to have a slightly more communal thing where everybody in the room exchanged shoes with somebody else in the room. So like I take my shoes off, I give them to you, and then you give your shoes to her, and so on. Everybody gets somebody else's shoes. Okay, it'd be like a character building exercise. So how many ways are there to do that? Any thoughts about that? How many ways can we have a shoe exchange in this room? What?
Is it 1 shoe for both?
Let's say that I give both my shoes to one person. So let's say that I tie them together and I give them to one person. So how many ways are there to kind of massively exchange all the shoes in the room with each other? Yeah?
If there's a person in front of another person, they could just pass their shoes back to the person in back of them, and so on and so on and so on. So by row.
So by row. Okay, so like starting from the bottom, you go up like that and then down. And okay, that's one way. Any other ways?
150 factorial.
150 factorial. Somebody knows about factorials. Let me. So, can somebody else explain that? Why 150 factorial? Yeah.
One person gives it to 149 people, then the other person gives it to 148, and so on.
Right. So now we have. So I have to choose who gets my shoes. So there are 150 ways for me to choose, including keeping my shoes. I might just want to keep my shoes. Okay. In fact, I think I will. Okay. So 150 for what I do. Then the next person who gives their shoes away only has 149 choices because somebody's already got shoes. So 149. And then the next person has only got 148 choices. And so on. And then until we get to the very last person who's actually got no choice left because everybody else is all set. So it's 150 times 149 times 148, 147, and so on. That's called 150 factorial. That's the symbol we use for this. And it's very big. How big is this number? Let's see. Is it bigger than the number of red blood cells in the room, for example? It is. It is. In fact, so here's like my lame attempt to see how big this number is. Almost all the numbers in this product are bigger than 10. Right? Except for the last 10, all the others are bigger than 10. So there's 140 numbers here that are at least 10. And I multiply them all together. This is bigger than 10 raised to the 140th. Everybody okay with that? 10 times 10 times 10, 140 times. So this number, the number of ways we can exchange our shoes, is bigger than the number of red blood cells in the room by a very, very large factor, because that was 10 to the 12th, and this is 10 to the 140. Okay? And it's also bigger than the number of atoms on the Earth, which I was going to talk about. So it's a really big number. And it's easy to make big numbers like this. All we have to do is come up with some crazy scheme for something complicated to happen and count how many ways it happens, and we get enormous numbers. So infinity is really far away because we can do all these things, but they're still finite. Okay, so one could have a whole different talk about this kind of thing, and but I want to talk about infinity. So let me start that part of the talk. So I have this slideshow. There will be a very short slideshow in a few minutes, but most of the talk is going to be on the board. Are there any questions so far? Okay, feel free to ask questions. I'll be sure to be making mistakes so you can catch them. Okay, so first of all, so people have thought about infinity for a long time. And as far back as the ancient Greeks, Aristotle distinguished between two different ways of thinking about infinity, which are going to kind of structure what I want to say. There's what Aristotle called potential infinity, and then what he called actual infinity. Okay, potential infinity is just the idea that there are things that we can keep doing, and there's no natural time to stop. There's no particular stopping point. You can always do more. So the first example of this is just counting. If you take, if you start counting, you keep adding 1, 4, 5, 6, and so on. There's no last number where you can't count anymore. There's always, whenever you have a number that you can write down, you can always write down one more. You get to very big numbers like this, right? But then you can write the next one, 150 factorial plus 1. And if you have enough time, you could write down all the digits, and you could do the arithmetic, and you could find the next one, and you can keep doing forever. But the distinction is you don't actually go forever. Nobody ever counts all of the numbers. You just know that wherever you are, you can keep going further. Okay? Whereas actual infinity is the idea, which is a little bit more slippery, of actually thinking about the infinite object itself. Like, think about all the numbers all at once. Or we'll talk about what this means. And whether or not this is a viable thing to do, the universe itself is finite. Right? At least, certainly everything we know about is finite. There's a question, I suppose, about whether the universe is infinite, but I'm not qualified to answer. So, in the presence of only a finite world that we live in, and we only have a finite amount of time, we never actually have an infinite object in our hands. So you could ask yourself, what's the point of even thinking about infinite objects? So I'm hoping to make that a little bit clearer. Okay, so that'll be the second part of the talk. Let me first talk about potential infinity, about doing things over and over again and learning something from it. So one version of this. Hi, come in. Hope you can find seats. There's some seats in the middle here and there, by the way, if anybody wants. Okay, so one way to talk about potential infinity is just counting. You can count all the numbers. You can count all the even numbers. You can always make another even number. You can always make another odd number. You can always make another prime number. That's actually a slightly deeper theorem, but still a very old fact. You can also talk about geometry, geometric shapes. And another kind of infinity comes from the idea of rescaling or zooming in. And so let me start with a very familiar thing. If I just draw a line and I put numbers on it at regular spaces, like this. Everybody familiar with this drawing? Number line? Right. So you can think about this as one static object, or you can say, what happens if I look at one piece of this and magnify it and look a little deeper? So for example, here's the interval between 3 and 4. I could look at it with a magnifying glass and make a bigger version of it, 3 and 4. And then I could subdivide it again. Let me try to subdivide it into 10 pieces. Okay. So that's about, let's pretend that was 10 equally spaced pieces. And I could pick one of them, let's say this one, and enlarge it again. Okay? I'm going to run out of space. Let me put it up here. So here's an enlarged version of this one. So this one went to here, and then this one, sorry about the bad use of the board, but this one, I'm going to make it bigger. What do I label these 2 points? Anybody know how to label these 2 points? Yeah? Yeah. 3.1, right. 3.1 and 3.2, so I can put that here. And I can enlarge it again, and I can again try to do this even intervals. So if I now pick a point, let's see, let's pick the 5th interval. I can keep doing this, right? Actually, let me, and then also, by the way, I can draw this one inside this one. It looks like this, if I do it right. And then I can draw this one inside this one. So in here I get, and then in this one I get this other one. Right? So this picture actually appears in here on a very small scale. And then in here, I can keep doing it and look at the next scale and so on. And if I, and this number is 3.14, and this one is 3.15. And I can keep zooming in and enlarging and zooming in and enlarging and keeping track by writing down these digits of which piece of the picture I was zooming in on. Okay? And you can imagine doing this without any natural time to stop. There's a kind of infinite process. And you can do it many different ways. I could have chosen lots of different intervals to zoom in on, and I would get different sequences, and I would zoom in on different parts of the original line. Anybody want to guess which number I had in mind when I was doing this? Wow. Yeah. Pi. Anybody else thought of pi? Yeah. Okay. So pi, we say that pi is equal to 3.1415926. Anybody else? 5? No, 3 is the next one, isn't it? 3. 3 is as far as I remember, because my calculator had this many digits. So it goes on forever, right? There's some kind of recipe. So this is a subtle point I want to make. We never write all of them down. There's a somewhat complicated recipe for figuring out what the digits are. And it's an infinite sequence. And even though we never write it down, we think of this potential process of generating all these digits. We can think of it as a number. And we can think of it as this kind of act of zooming in at some place in this line. So there's an infinite set of rescalings. Okay? So that's one kind of infinity. I wanted to draw some pictures for you of some other things. Question? Yeah. Where? Yeah.
So that segment,
Yes.
we consider that finite because it has a beginning and an end, or
You mean like this one, say, or?
3.14 to 3.115 to 3.15?
Yeah. So the segment has a finite length,
Okay.
but it has infinitely many points in it. All the points I drew plus all the points I'm going to keep drawing if I keep going. There's infinitely many places I can look. So
The segment itself.
the segment itself has a bounded size. So you think, so there are different things you can measure that could be finite or infinite. One of them is the length of something. The area could also be something you measure, and the number of pieces of it is a different one. Okay. Let me just check if I'm doing okay on time. Okay, so as usual, I'm running behind, but I always do that. I wanted to give you another example. I'm going to run through this quickly just because it's a little bit of a side trip. This whole talk is a bunch of side trips because infinity shows up everywhere in mathematics, and you can kind of talk about it, with respect to anything. So this is, whoops, yeah. So, sorry. Okay, this is a different way of zooming in on a number. So here I've realized a number x as the ratio of one side to the other side of a rectangle. I wrote a 1 by x rectangle. Okay, so I'm thinking of that shape of the rectangle as related to this number x. And then if I want to figure out more about the rectangle, I could try to cut it up into squares. So I could put a square in, another square, and another square, and another square. And then I'm out of room for squares, right? So if that was all there was, if there was no gap here, then this would just be 4, right? 4 by 1. It would be a 4 by 1 rectangle. But now I could fit in squares. I have now a kind of a thin rectangle. I can put more squares into that one. I get 3 in before I run out of room. And so this little one, if there was no gap, then this would be a 1 by 3 square, a 1 by 3 rectangle. But it's flipped the other way. So instead of being 3 over 1, it's 1 over 3. So I would have to add a 1 over 3. And my number would be 4 plus 1 over 3. But now I do have a gap. So I could fill this one in with squares. So let me do that. I can fit one square in. And then I'm out of room. And then I have to correct the 3 by adding the 1 square. Okay? So I should have said before, if you're not keeping track of the algebra, don't worry, because this is just this is just for fun. So I have a couple more steps of this. So the last rectangle there, I can fill it up with 2 squares. See the yellow squares? And then I have to correct the one that I had with another. It was a 1 by 2 rectangle that I would have put in. And then there's still room there. You see the little bit of room there? So I'm going to fill that in up with 3 squares. And so then I get 1 over 3. And then if there's more stuff to do right in there, then I could add more to this. So you could imagine, so the point of this whole example is this rectangle, which we think of at first as some kind of finite object, has an infinite kind of internal structure, which we see by trying to subdivide it into squares. And so this process of filling up with squares, it might end. It might be that at some point everything clicks into shape, and we're done, and there's no more gap. And then this expression would end, and we would have this expression, which is called the continued fraction expansion for a number. Or it could go on forever, like we could be spiraling in there, and there's always a gap, and we always add one more thing. And then we get an infinite expression, which is different from what we had on the first part of the board. And that's called again, it's the continued fraction expansion of a number. There's a famous one. Let me finish this with one more example. If at every step you just did 1 square and then you ran out of room, so that's this, you have a square and a gap and a square and a gap and a square and a gap, then you get this very nice spiral. And the number that you get here has a famous name. It's called the golden ratio. And it has this continued fraction expansion, which has all 1s. So this number phi, which maybe some of you have heard of, the Greeks love this number because it makes a rectangle that has a very pretty shape. The Parthenon is supposed to have roughly this shape, more or less. People like to say that it sort of shows up in all of classical architecture. I'm not completely convinced. But this number has this very infinite kind of structure, which we can study. So that's another example of infinity. And I was going to give you more geometric examples. So here's another one. This is a picture by Escher. Everybody heard of Escher? Some of you have heard of Escher. M.C. Escher was an artist, a very good graphic artist who got in some bad company. And he was talking to Coxeter, who was a mathematician, and he learned about various things. So this is an example of a tiling. You see the angels and the devils. The devils are the black shapes, and the white shapes are the angels. And they're tiling some pattern. So what do I want to say about this? A couple of things. One is, it's not an infinite picture. Escher is, well, he's dead. And before he died, he only had a finite amount of time. So he only drew, I guess now, I don't know what he's doing now. I have no comment. But he only drew a finite number of shapes in this picture. Okay? But it suggests the picture is not just a picture. There's a recipe for how to make these shapes. And the recipe has no stopping point. If you keep going, you will get more and more along the boundary here. You'll get more and more of these shapes. And it's another example of a procedure which has no natural end. And so it corresponds to what we call an infinite tiling in mathematics. And one more thing to say about this is that you can interpret this picture in two different ways. You can interpret this as a shape that fills out the disk and the tiles get smaller and smaller. So in some sense, the infinity is coming in when you have smaller and smaller things nesting in on the boundary here. Or there's another interpretation of this in which it's a perspective picture of a particular space called the hyperbolic plane or the non-Euclidean plane, which is an infinite space. And in that space, all of these shapes have the same size. And this is just a particular perspective view of that space in which the horizon is here. And if you kind of squint your eyes, you can kind of imagine that you are flying above this infinite plane, and you can just go to the horizon and see these infinitely many shapes coming at you. Okay, so that's a two-dimensional tiling. Here's a three-dimensional tiling. Those of you who were at my lecture last year saw this picture because I like this picture. So I try to find excuses to put it in. So this is a three-dimensional tiling. So if you look carefully, you'll see that there's a kind of dodecahedron in the middle of this, and then on attached to its edges are more dodecahedra, and they keep going out away from you into space. This is another one of these non-Euclidean spaces. And again, things look like they're getting smaller, but actually they're just getting farther away. Okay, so it's some kind of perspective picture. And again, there's a recipe for doing this over and over and over again. Okay, everybody happy with that? So the next picture, well, I guess is the universe, or stars in the universe. And I put this picture up because actually it's probably not an infinite picture. Although it's very big, and we'll never get all the way to the end of it. The stars are very far away. And you can also imagine if you get better and better telescopes, you could zoom in on this, and you get more and more finer pictures of what's in there in any part of the picture. But there's no recipe for going on forever. And it's some kind of question about astrophysics, whether the universe does or doesn't go on forever. But this is in some sense a finite picture, and the other pictures I showed you are infinite pictures in the sense of potential infinity. One last, let me do a last guided tour of a potentially infinite picture. This is called the Mandelbrot set. And this is a set so I'm cheating a little bit. I'm not telling you how this is done. And you should feel cheated. So there's a beautiful piece of mathematics which explains what this means and how one builds it. But the thing I want to say about it is that there's a recipe. If I pick a point on the screen, there's a recipe for figuring out what color to color that point. And that recipe generates this shape. And the recipe goes on forever. So I actually had to look on the web for, let me find this, for an app that actually does this. So here's the same picture, but with the app of a mathematician named David Eck. And let me zoom in on it. So you see that it's the same picture, but now I have the ability, let's pick a spot. Everybody see what I'm doing? I'm going to pick, say, this spot and zoom in on it. And then I can maybe pick this spot over here and zoom in on that. Okay? Now the recipe is such that the more digits you have and the finer your scale, the longer it takes to figure out what's going on, what the color should be. So I have to change the numbers that the computer uses to get a better picture. So here's a finer picture of the same spot. And now I'm able to zoom in some more. So let me zoom in here, maybe. And then maybe here. And then one more time. And then I think I have to change the accuracy again. Okay. Now you see, okay, you get the idea? So not only can you zoom in a lot, over and over again, when you zoom in enough, you see more copies of the original thing. And in fact, there's a theorem that the entire thing exists as a copy inside of itself. And so in here is all of the complexity you saw outside is again replicated inside, and you can keep going. You can sort of zoom in. This is a good thing if you have a couple of hours to kill. You can do this. You can sort of go, wherever you like, and keep looking, and get more and more complexity. Okay. So again, I have to stop at some point because the lecture only lasts so long. But there's a recipe which goes on forever. So we talked for a while about potential infinity, about different kinds of pictures we can draw, different kinds of ways we can think about numbers and how they describe geometric shapes. So let me now go to the other side, the side of of actual infinity. Okay, so infinite sets. So let's think for a few minutes about what it might be to have an infinite set. Oh, actually, wait a minute. There was one other thing I wanted to do. Yeah, let me do one more puzzle just to kind of bridge the gap between doing something potentially infinite and actually doing something infinite. So let me describe a game to you. Okay. So the game is this. I have a basket. So you need two players in this game. So player 1 has a basket, and player 2 has a lot of ping pong balls. Okay? In fact, there are infinitely many ping pong balls. I'll be player 1. I'll be this player. I'll have a lot of ping pong balls, and one of you will hold the basket. And the basket can hold infinitely many balls, and I have infinitely many balls over here. And here's how the game works. Okay? It's my move. I put in 10 balls. Okay? I'm going to draw 10 balls. It's hard to draw 10 balls, but here it is. Okay? And then it's your move, and you get to remove one ball. So you take one ball and take it out of the basket. Okay? And that's the game. Next time the game now goes on, I put 10 more balls in, and you get to take one ball out. Okay? And we play the game over and over again. In fact, we play an infinite number of moves. Okay? I put in 10 balls, you take out one ball. So the question is, and this is why I want to start talking about actual infinity, what happens at the end of the game? What's in the basket at the end of the game? Any thoughts? Yeah. There should or shouldn't? There should. So you're saying infinite. So at the end of the game, so what you're suggesting it should be an infinite number of balls in the basket. Okay. Any other thoughts on this? Yeah.
Shouldn't there be no end to the game? Because you said infinite amount of moves.
Shouldn't there be no end to the game? Yeah, that's another thing. Right. So no end to the game. Right. It's a good question. So I'm trying to get beyond the infinite thing and find out what happens at the end of it. And the point is, it's hard to say what happens. So this is part of the question. Yes?
Well,
Yeah.
Really, it's not infinite number of balls in the basket. It can't be. You keep on taking out one, so then it would be infinite amount of balls minus one for every
Oh.
ball you put in.
So you're saying I'm always taking out one. So I'm taking out an infinite number of balls. And I'm putting it in an infinite number of balls.
Because so then they could be
So what do you think should be left in the basket?
infinite number of balls, but minus one. I don't know how to say it because
Okay.
you can't really.
Okay. That's good. There was some, yeah. But,
Infinity minus infinity is infinity. Infinity plus infinity is infinity. So there's no theoretical.
let's see. So you're writing this, and you're writing this. You're telling me to write these things. I'm not sure I agree with you, but I'm writing them down. So you're saying infinity minus infinity is infinity. Well, I'm not sure why you're saying it, although there's an argument for it. I think you're suggesting that algebra may not give us the answer we need. Is that what you're saying? Okay. Wait, there was somebody over here who had, yeah.
Because you ended it, it would really depend on how many times you play.
On how many times? Right. So okay, let's see. If I play once, how many balls are in here? 9. If I play twice, how many balls are in the basket? 18. So if I play 100 times?
900.
900. Okay. So as I play a finite number of moves, the number of balls gets bigger and bigger. We all agree about that? But it's always finite. So after a finite number of steps, I have a finite number of balls, and the finite number gets bigger and bigger all the time. Yeah.
So I'm thinking, like, if you wanted to find, like, one ball out of, like, the infinite number of balls over there, you could try, because first you take 10 out, right? Each time.
Yeah. Take 10 out.
So you could do 10C1 divided by infinity C1. Like, I'm thinking, like someone said, like, combinations and permutations.
Well, we talked about combinations before, but I'm not counting the number of ways I can do it. I'm asking how many balls are left at the end. But yeah, you were next to, yeah. Yeah, so after finally, so let's write down. After n rounds, we all agree we should have 9 times n balls in the basket, right? And now I'm trying to ask this kind of, maybe it's not a nice question, maybe it's a bad question. What happens after infinitely many rounds? So actually, let me suggest the following interpretation of the game. I could start, instead of doing just this game, before I play the game, let's number all the balls. 1, 2, 3, and so on. Okay? And let's talk about which balls are actually in the basket by number. So after the first round, well, let me just write them down. So we could play the game as follows. We could say, I'm going to put in balls numbers 1, 2, 3 through 10 in the first round, and you're going to cross one out. Okay? Let's cross this one out. Okay? In the second round, I'm going to put in 11, 12 through 20, and you get to cross one out. So you could cross this one out. Don't have to, but suppose you do. And then the next time, I'm going to put in numbers 21, 22 through 30, and you're going to cross this one out. But suppose we play the game that way. Okay? I put the balls in like this, with these numberings, and you cross them out. You sort of ignore the fact that I'm winning. Okay? And you cross them out in the beginning because you're very patient. Okay? After 10 rounds, you've crossed out the first 10, and I've put in 100. So here's the point I want to make. No ball on this list stays in the basket forever. Every ball, like say ball number 29, okay, it'll get crossed out. After 29 moves, this ball will get crossed out. So if you're asking yourself, after infinitely many moves, which balls are in the basket, the answer is none. None of the balls. Okay? On the other hand, if you play the game this way, if you crossed out number 10, then number 20, then number 30, then a lot of balls would stay in the basket after all the moves are done. So if I erase all the, so here's the question, if I erase all the numbers, what really happens? Yeah? Nothing is the right answer. Yeah, yeah. What really happens is I run out of balls, right? That's what really happens. So math is not about what really happens. Math. You shouldn't quote me on that. No, math is about the patterns, and the lesson to take from this is that if we're describing some kind of an infinite pattern or infinite process, we have to be very careful exactly what we mean. Okay? And if I tell you, if I describe the game the way I first described it, you put the balls in and you take some out, and I didn't tell you how you're doing it, and I want you to think about an infinite number of moves, I have not told you enough about the game. If I describe the game in this level of detail, then I can answer the question. And then if the question is which balls are left, I can answer that question. Okay? All right, so that's our practice about why it's tricky to think about infinite sets. So let's go on with that theme. So let's name some infinite sets, just so we can start to be more concrete. Well, maybe this was concrete anyway. So the one infinite set we've been talking about this whole time is the set of natural numbers. The set, I'm going to write it like this. It doesn't look that different from what I wrote before. Except for one thing, I kind of put braces around it. So that's just my signal that I want to think of it as one big basket full of things. I'll also give it a name. It's usually named n by mathematicians. It stands for natural numbers. So these are the numbers you use to count. It's clearly an infinite set. Okay, another infinite set is what are called the integers. So if I take these guys and I include 0, and I also include both the pluses and the minuses, 2 and minus 2 and 3 and minus 3. I'm not writing this in order of the number line, but I'm just writing it. Okay, all of the integers, you all know how to write down integers, right? You write down a bunch of digits from 0 to 9, and you put a sign in and so on. Everybody knows how to deal with these things. And there's infinitely many of them, in some sense. And we call that set Z. Z comes from the German word Zahlen, which means number. So these are the integers. Okay, one more. Anybody have another infinite set for me while we're at it? Yeah. The real numbers. Actually, that was my fourth one, so let's put that over here. The real numbers. I don't have a way to write them as a list, but I'm just going to say all the numbers on the number line. And we talked about actually how to express them as infinite decimal sequences, right? Were there other, let's see, you had a...
All fractions.
Fractions. The fractions are called Q. So these are all the things of the form, you know, say 3 over 5 and 1/2 and negative 167 over 422 and so on, right? Everything of the form P over Q, where P and Q are integers. Okay? P and Q are integers. Okay? And these are called the rational numbers or the fractions. And it's already an interesting fact. So all of these sets I produced live on the number line. We think of them geometrically. Let me draw that picture one more time. So here's the number line. The integers are nicely spaced along the number line like this, and the negative ones go like that. And then, so that's these first two. And then the fractions show up all over the place, like here's 1/2, and here's 3/2, and are there any other fractions? I don't know. How about 2/3? 2/3. Where is that going to be? Over here, right? Okay. So everybody knows some fractions, and there's negative fractions, right? Here is, I don't know. Here's negative 9/10. Okay, so the fractions are kind of densely organized in here. They're everywhere you look, no matter how deep you look, there's a fraction there, right? So they're everywhere. Is there a question? Yeah.
Another set is the imaginary numbers.
The imaginary numbers, that's true. I'm going to not talk about them today, but I'll mention them. So imaginary numbers. Right. You might wonder whether maybe all the numbers are imaginary after all this, but right. There's a specific set called the imaginary numbers, but that's a great subject for a different talk. Well, actually, they're going to come up in some sense. Okay. So what's the difference between these and these? Well, it actually took a while to realize that there are numbers that are not fractions. The ancient Greeks realized this. That wasn't so long ago, only a couple of thousand years ago. They realized, so the ancient Greeks realized that if you, after they proved the Pythagorean theorem, they realized that if you take a triangle with 45-degree angles and edge lengths 1, then the hypotenuse must have the property that its square is 2. It must be the square root of 2. So they realized there has to be a number, if you think of this as a copy of the number line, there has to be a number whose square is 2, and then they started trying to figure out what fraction it was, and they discovered you couldn't write it as a fraction. No fraction could have the property that its square is 2. And so they realized that there were numbers that were not fractions, and they considered this to be a great secret, and they kept it hidden. But eventually it was, became part of mathematics. And in fact, the square root of 2 is what's called an irrational number, and it lives on this bigger set of all numbers on the real line. Okay, there are other infinite sets. Just to kind of go back to my tendency to draw pictures, we could take the plane. Here's the plane. Right, this is just supposed to be, think of the plane of the blackboard, okay? But it's an infinite plane. It goes on forever. It goes past the blackboard. It goes through the wall into the next building and gets all the way to Harvard. And that's the plane, right? The infinite plane. And in the plane are many points. There's infinitely many points in the plane. It's like a two-dimensional version of the line. In the line, there are all these points. In the plane, there's all these other points. It contains a copy of the line. Okay, that's another infinite set. Yeah? Is a question? No? What? The complex numbers. Yeah, actually, so somebody mentioned imaginary numbers, and the imaginary numbers and the real numbers together produce a set called the complex numbers. And actually, it turns out the complex numbers describe the points in the plane. So there's a connection between the plane and the complex numbers. But we're not going to talk about that today. And in the plane, okay, so the plane is another set with infinitely many points in it. Here's another set with infinitely many objects in it. Suppose I draw all the lines in the plane. There's lots of lines, right? So the set of all lines in the plane is an infinite set. I could make lots of lists of lines, and then I wouldn't be done. I could make more lists. So there's an infinite number of lines in the plane. And while we're at it, just to kind of remember that there's kind of an infinite amount of stuff you can do in math, I could think about other things in the plane. I could draw the set of all circles in the plane. That's an infinite set. I could draw the set of all squiggles in the plane. I could draw the set of all collections of dots in the plane. So the set of all subsets of the plane is a set. So let me just write that down. So there's the set of all subsets of the plane. In fact, that's a huge set. If you think about what kind of configurations of points can there be. It's like the two volunteers in the beginning, right? There's the set of people in the room, and there's the set of groups of 2 volunteers in the room. There's also the set of possible teams of 3 volunteers in the room, and the set of all possible teams of 5 volunteers. And this is the set of all possible configurations in the plane. Yeah, was there a question?
Oh yeah, I was going to go back to oh yeah, so I was thinking the permutations, combinations are more like possibilities. Like
Right.
two out of however many people are in the room.
Yeah. Right, so we did that. The combinations formula gives you how many teams of 2 you can choose out of a set of people. Here now everything is infinite, so there's not a formula like that, an algebraic formula to say what the number of, in fact the number of subsets is still an infinite number. So let me, in the time we have left, which is maybe 15 minutes, let me try to talk about something that I've been kind of skirting around. All these infinite sets, with finite sets we kept talking about which ones are bigger than others. And with infinite sets, we haven't addressed this question. So let me ask this question and try to tell you a little bit about it, although we'll see how far we get. So the question is, are all infinite sets the same size? So there's a problem with this question. What's the problem with the question? They're all infinite, yeah. Yeah?
There's different sizes of infinity because you take the set of reals versus the set of odds, it's a larger set, the set of reals.
So you're saying that this set is bigger than this set, say?
Yes.
Yeah. Well, so actually you're right, depending on, but the point I want to make is that I haven't told you what this word is supposed to mean. And I don't think anybody has said anything about what this word means. What does it mean to talk about the size of a set? And this is the point I want to make. So,
Are you referring to one being a subset of the other?
it's close to that, but not quite. Let me say, let's make like an attempt. Let's make an aborted attempt to think about what size of infinite sets is. So inside the natural numbers are the even numbers. Right? So the even numbers, so here's a thing you could observe. The even numbers, here they are. Right? And so on. All the even numbers. This set is inside, here's the symbol for inside. It's a subset of the set of all numbers. So you could say this is a smaller set. In fact, it looks like it's a lot smaller because there's lots of stuff left over, like the chairs. Could we say it's half? Could we say that this has a size that's half of this? So we could try to do that because, like we said, you could fit these in here, and there's a gap of 1 for every one you put in. But it's not clear that half is the right number because you could put these in a different way. You could, for example, you could make number 2 sit in its place. That's number 2. But you can also decide to put it somewhere else. Let's take number 2 and have it sit in chair number 3. And put number 4 in chair number 6, and put number 6 in chair number 12, and now there's a lot bigger gaps, and we can still put them all in. So it looks like there's lots of different ways to put this set inside this set. Moreover, there's a way of putting this set inside this set. If these are people and these are chairs, then number 1 can go into chair number 2, and number 2 can go into chair number 4. Let me draw the arrow. So 1 goes to 2, 2 sits down in 4, 3 sits down in 6, whoops, 4 sits down in 8, and so on. Every number, n, sits down in chair number 2 times n. And now we filled up all the chairs on this side with people from that side. And so it looks like that set is smaller than this set. Well, or the same size. So infinite sets can go into each other in different ways. And it could be that one set can go into the other set and vice versa. So let's see. So this tells us, well, this tells us we have to be careful. So George Cantor, let me write his name. He was born, I think, in 1845 and died in 1918. Thought about this a lot. He sort of introduced a systematic way of thinking about infinite sets into mathematics. And he came up with a definition, for a good definition for the size of an infinite set, which allows you to actually think about them in a productive way. And the definition was this. He said that A and B, two sets, have the same size if there exists a perfect matching between them. And I'll tell you what this means. Perfect matching, it's not very complicated. So let me just draw you the picture. Here's a set A, and here's a set B. So visualize them as just a bunch of items, okay, like numbers or whatever examples we had over there. A perfect matching is a way of, if you think of A as people and B as chairs, it's a way of giving everybody exactly one chair and filling all the chairs. So you have to take every point in one set and find a target point in the other set. And you have to be able to do this for every one of them. And there's no collisions, so no two arrows collide on this side, and no two arrows emanate from the same point. So this is not allowed, and this is not allowed. Okay, those don't happen. So every point gets a place to be, and no 2 points collide, and every point is covered. So every point on the target gets an arrow. Okay, that's a perfect matching. Everybody clear on the idea of a perfect matching? Okay, so in fact, so if you make this the definition, it captures the idea of size of finite sets that we're used to. If you had two sets, like a set of, well, chairs and people in the room, and if you could make a perfect matching, then you would know they have the same number. So this exactly fits our notion for finite sets. For infinite sets, it seems to be, it's at least a definition. You could think about it. It might not be very interesting, though. Maybe you would find out that every two infinite sets have the same size. So the interesting part is that A, you can do this. I'm running out of time, so I'm not sure how many of these examples I can give you. So let me say a few things about what sets have the same size. Maybe we can, now we've been talking about it for a while, we can think about why it's all true. So the set of integers, the set of counting numbers, the natural numbers, has the same size. Let's use this little symbol to mean the same size as. Okay, this means same size. So the natural numbers have the same size as the integers. Is that clear to everyone? Maybe we should. In fact, I kind of showed you when I wrote them down. The natural numbers you write like this, maybe. And the perfect matching can work this way. 1 goes to 0, 2 goes to 1, 3 goes to -1, 4 goes to 2, 5 goes to -2, 6 goes to 3, 7 goes to -3. Everybody clear about what I'm doing? Okay? So it's a perfect matching between just the natural numbers and the integers. So these are the same size. Maybe more surprising is that these are the same size. Who is surprised by this? 1, 2. Everybody else is not surprised? Wow. Okay. So it's obvious that these are the same size. There's no reason. So it's not. So let me say for 10 seconds why it's surprising. It's surprising because if you think about the geometry of the natural numbers, 1, 2, 3, they go off this way along the line. And then the rational numbers, the fractions, they're everywhere. They're all over the place. How could you possibly find a matching between these numbers and all these numbers that are all over the place? They could possibly work. So, so you might be great. This should obviously be bigger than that, because you can't possibly match these natural numbers to this. So let me show you how you do it quickly. So I'm going to draw a chart of all the fractions. So I'm going to write down, let's just do this for the positive fractions, just to kind of make it, just to do an easier case. So let's look at all the natural numbers here and all the natural numbers here again. Make a little chart. And in here I'll put in 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. And then 2 over 1, 2 over 2. Everybody see what I'm doing? 4, and then let's just do a couple more. 3 over 1, 3 over 2, 3 over 3, 4. Okay, so this grid gives me all the positive fractions. Actually, if you're paying careful attention, you'll see I've overcounted a little bit, because these guys are the same. They give me the same number. So let's pretend we didn't notice that, because it's a slight complication. So now I want to attach this grid of infinitely many things to the natural numbers in a perfect matching. And here's how I'm going to do it. I'm going to draw diagonal lines. So this one is a diagonal line with one point in it. Here's another diagonal line. Here's another diagonal line. You see what I'm doing? Whoa, this is a diagonal line with more points. And I'm going to count this way. 1. I need color for this. This is why I brought color. By the way, the reason I became a mathematician is so I could use color charts. Forgot to mention that. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. 11, 12, 13, 14, 15. You see what I'm doing? So I'm getting a perfect matching between the natural numbers in yellow and the fractions in white. Okay? Now, okay, and then I'll leave you guys to figure out what to do about the fact that some of the fractions are kind of twice. So this shows you that these two things have the same sign. Okay, so we have a couple minutes left. Maybe less than a couple minutes. Let me finish with one last thing. So there are many things one can say about this, but I cannot, I think it's actually probably illegal for me to tell you this without telling you the last bit, which is that there are infinite sets of different sizes. Okay? If there weren't infinite sets of different sizes, this would not be an interesting subject. So the other thing that Cantor proved, which is sort of what got him in trouble, he was actually a little bit controversial at the time, was that he proved that the natural numbers, which are the same as the rationals and the same as the integers, are not the same size as the real numbers. There are a lot more real numbers than there are natural numbers. And so let me give you the proof, because you can give it very quickly, and then it gives you food for thought. So this is if you think about this, it's a much harder thing to do than what we just did. Because I proved to you that these are the same size by showing you how to match them up. Once I convince you that there's a matching, we're done. Right? I just explain this matching, and it's there. Now we know it's there. To prove that they're not the same size, I have to prove that there is no matching. That no matter how clever you are, whatever you do, it can't work. Okay? So in the last minute of the lecture, let me explain why there cannot be a matching between n and r. Okay? So the way you do this, how do you do this? Well, you imagine that somebody has given you a matching, and you prove that they must have made a mistake. That's what you do. So let's imagine, suppose we have a matching. So what does that mean? It means that for the number 1, we have a real number. Let's actually, just to make our lives easier, assume all the real numbers are between 0 and 1. It makes the discussion easier. So suppose for 1, we had, say, this number. Here's a real number that shows up here. This is just supposed to make you think of some real number. For 2, we had a different real number. Maybe it was 1, 4, 1, 5. You might recognize this real number. 5, 3, and the rest. Okay, so there's a number like that. There's another number. I don't know. There's lots of real numbers, and suppose somebody has come up with a list of all real numbers. So each one is a string of digits. Perhaps they end in zeros, right? It might be finite after a while, or maybe not. Maybe this one is just ones. Maybe this one is like 5, 4, 5, 4, 5, 4, and they just repeat. There's lots of different possibilities. And somebody comes to you with this list and they say, this is it. It's a list of all the real numbers. It's a matching between n and r. Okay? So you could do the following. Now we'll use green. You can say, well, I'm going to build a number that's not on your list. I'm going to make a number that you missed. And here's how I'll do it. I'm going to circle the first digit of the first number, and the second digit of the second number, and the third digit of the third number, and the fourth digit of the fourth digit, and so on. I can go on forever like this, right? Right? I circle the nth digit of the nth number, and then in green, I choose a digit different from the one I see. So I'm going to replace this 1 with a 6. I'm going to replace this 4 with a 2. I'm going to replace this 1 with, I don't know, 0. I'm going to replace this 4 with a 5. See what I'm doing? This is what you do when your parents give you rules. Okay, you go to each part of the rule and you change it a little bit. So the new number, the green number I wrote, 6205, it's not on the list. You see that it's not on the list? It can't be the first number because it differs in the first digit. It can't be the second number because it differs in the second digit. It can't be the third number because it's different in the third digit, and so on. So no matter where we are on the list, the green number doesn't match the white number on that line. And so I found a number that's not on your list. Okay? Now, that's the proof, actually. That's the proof that there's no matching. And, well, I mean, you could think, this is actually worth thinking about, because you could look at this and say, well, that's stupid. I could just take the green number and add it to the list. What's the big deal? But, you know, you'd have to add it somewhere. So maybe you'd add it over here, between these two. You get a new list. I could just go to your new list, and I can find a number that's missing from your new list. There is no list that doesn't have a gap, that doesn't miss some numbers. And so, in fact, it's missing a lot of numbers. Okay, so that shows that R is bigger than N. It's uncountable. Another way to say this is that the set of all real numbers is uncountable. You cannot count them using the counting number. And then Cantor went on to prove other things with this. We can prove that lots of, I mean, it shows up, in fact, everywhere in mathematics, that when you have a countable set, it's much smaller than an uncountable set, and this is actually plays a big role in mathematics, and I don't have time to tell you about it, but maybe I should end here. So I'll finish by saying that the reason that we have to think about infinity in mathematics is because we have to study patterns that don't stop, and we have to be able to say what to do when we don't know how to stop. Nevertheless, we have to stop. So.